There are two methods to balance redox equations: the oxidation number method and the half reaction method, also known as the ion-electron method. The oxidation number method is based on the change in the oxidation number of the reducing and oxidizing agent. The half reaction method is based on splitting the redox reaction into two halves, the oxidation half and the reduction half. Let's discuss the various steps to balance the redox equation using the oxidation number method with the help of an example. In this reaction, permanganate ion reacts with bromide ion in basic medium to give manganese dioxide and bromate ion. In the first step, write down the correct formula of all the reactants and products in the reaction. The second step involves assigning the oxidation numbers to all the elements in the reaction and also identifying the atoms which undergo change in the oxidation number. We know that in polyatomic ions, the sum of the oxidation numbers of all atoms in the ion is equal to the charge on the ion. Thus, the oxidation number of manganese in permanganate ion may be calculated as follows. Let the oxidation number of manganese be X. We know that the oxidation number of oxygen is -2. Hence, X plus 4 multiplied by -2 equals -1. Therefore, X equals to +7. Thus, the oxidation number of manganese is +7. We also know that the oxidation number of a monoatomic ion is same as the charge on the ion. So, in the case of bromide ion, the oxidation number will be -1. Now let us focus on the products. First, we'll calculate the oxidation number of manganese in manganese dioxide. We put the oxidation number of manganese as X. X plus 2 multiplied by -2 is 0. So, X plus -4 is 0. Hence, X equals +4. Next, we'll calculate the oxidation number of bromine in bromate ion. Let us consider the oxidation number of bromine in bromate ion as X. X plus 3 multiplied by -2 is equal to -1. Thus, X is equal to +5. Now, observe the change in the oxidation number of the elements. The oxidation number of manganese changes from +7 to +4, and the oxidation number of bromine changes from -1 to +5. Note that oxygen does not undergo any change in oxidation number. In the third step, calculate the total increase or decrease in oxidation number per atom and for the entire molecule or ion in which it occurs. If the increase or decrease in oxidation number is not the same, then equalize them by multiplying with suitable coefficients. In this case, the decrease in oxidation number of manganese is 3, while the increase in oxidation number of bromine is 6. Hence, to make the decrease equal to the increase, we multiply the decrease in oxidation number, that is, 3 with 2. Which means that we introduce a coefficient of 2 with manganese on the left and the right-hand side of the equation. Now, let's come to the fourth step. Identify the involvement of ions and balance the ionic charges. If the reaction takes place in water, then add H plus or OH minus ions on the appropriate side, so that the total ionic charge of reactants and products is equal. If the reaction takes place in an acidic solution, then add H plus ions. If the reaction takes place in a basic solution, then add OH minus ions. As the reaction occurs in the basic medium and the ionic charges are not equal on both sides, we need to add 2 OH minus ions to the right side of the equation, so that the ionic charges are balanced. Finally, balance the number of hydrogen atoms. This can be done by adding H2O molecules to the reactants or products as applicable. In this case, we have 2 hydrogen atoms on the right-hand side and no hydrogen atoms on the left-hand side. Hence, add 1 water molecule on the left-hand side to balance the hydrogen atoms. Now, also check the oxygen atoms. If the numbers of oxygen atoms on the reactant and product side are same, then we can say that the equation represents a balanced redox reaction. In this case, if we count the number of oxygen atoms on either side of the reaction, we can see that there are 9 oxygen atoms present on either side. And thus, the equation represents a balanced redox reaction. The half reaction method is based on the principle that electrons lost during the oxidation half reaction are equal to the electrons gained during the reduction half reaction. Let's look at an example. In this reaction, dichromate ions in aqueous acidic medium reacts with ferrous ions to give ferric and chromium 3 ions. Let's look at the steps involved. First, write the skeletal equation for the reaction in the ionic form. Then identify the species which have been oxidized and reduced, and split the reaction into 2 half reactions. This is step 2. In this case, the oxidation number of chromium decreases from +6 to +3. Thus, dichromate ion is reduced. Simultaneously, the oxidation number of iron increases from +2 to +3. Thus, iron is oxidized. Thus, the 2 half reactions can be written to show the oxidation half reaction and the reduction half reaction. In the third step, balance all atoms except oxygen and hydrogen. In this example, the oxidation half reaction is already balanced since the numbers of iron atoms are equal on either side of the equation. In the reduction half reaction, there are 2 chromium atoms on the left-hand side and only 1 on the right-hand side. So, we'll multiply Cr3 plus by 2 to get 2 chromium atoms on the right side too. Now in the fourth step, balance the H and O atoms. If the reaction takes place in an acidic medium, add H2O to balance O atoms and H plus to balance H atoms. If the reaction takes place in a basic medium, add H2O to balance oxygen atoms and OH minus ions to balance hydrogen atoms. In this case, in the oxidation half, there are neither oxygen nor hydrogen atoms. But in the reduction half, you can see that there are 7 oxygen atoms on the left-hand side, but no oxygen atom on the right-hand side. As the reaction occurs in acidic medium, to balance 7 oxygen atoms on left-hand side, we add 7 H2O molecules on the right-hand side. Now, after the addition of 7 water molecules, there are 14 hydrogen atoms on the right-hand side, but no hydrogen atom on the left-hand side. Hence, to balance the hydrogen atoms, we add 14 H plus ions on the left-hand side. In the 5th step, balance the charge by adding electrons to one side of the each half reaction. If required, make the number of electrons equal in the 2 half reactions by multiplying one or both half reactions by appropriate coefficients. The charge of iron on the right-hand side is +3, while on the left-hand side it is +2. Therefore, to balance the charge, we will add 1 electron to the right-hand side. In the reduction half reaction, there are net 12 positive charges on the left-hand side and only 6 positive charges on the right-hand side. Hence, to balance the charge, we add 6 electrons on the left-hand side. To balance the electrons lost in the oxidation half and gained in the reduction half, we multiply the oxidation half by 6. In the 6th step, add the 2 half equations to obtain the overall reaction and cancel the electrons on each side. Thus, we obtain the net ionic equation as shown. Finally, verify the equation by ascertaining that the same type and same number of atoms and charges exist on both sides of the equation. Since the charges on both sides are equal, this is a balanced redox equation. Titrations that involve oxidation, reduction reactions are known as redox titrations. Redox titrations are used to determine the strength of a reductant or oxidant by using a redox sensitive indicator. Redox titrations can be performed using oxidizing agents such as potassium permanganate, potassium dichromate, and iodine. Let's look at each of them. Potassium permanganate is a dark, purple-colored liquid and a versatile and strong oxidizing agent used in the estimation of many reducing agents such as iron +2 ions, oxalate ions, etc. Indicators are not used in these titrations as potassium permanganate acts as a self-indicator. During the titration between potassium permanganate and a reducing agent, the pink color of potassium permanganate is discharged till the reductant is completely oxidized. A further addition of a single drop of potassium permanganate gives a tinge of pink color to the solution. This indicates the end point of the titration. In the redox titration reactions, where the oxidizing agent doesn't act as self-indicator, indicators such as diphenylamine or N-phenylanthranilic acid are used. These indicators are oxidized immediately after the last bit of the reactant is consumed, producing dramatic color change. For example, in the estimation of iron using potassium dichromate, diphenylamine is used as an indicator to detect the end point. In this reaction, Potassium dichromate oxidizes diphenylamine just after the equivalence point to produce violet blue color, thus indicating the end of the titration. The other class of titrations, which include iodine as the oxidizing agent, are iodimetric titrations and iodometric titrations. The titrations in which iodine is directly titrated against a reducing agent are called iodimetric titrations. For example, in the estimation of hypo or sodium thiosulfate, iodine directly reacts with sodium thiosulfate in the presence of starch as an indicator and produces an intense blue color. Iodometric titrations, on the other hand, involve the addition of an oxidizing agent to excess iodide ions to produce iodine, which is then titrated with standard thiosulfate solution. For example, in the estimation of Cu+2 ions, iodine is liberated by oxidizing iodide ions from potassium iodide. An intense blue color develops when starch solution is added to the liberated iodine. This solution is titrated against sodium thiosulfate solution. The color disappears as soon as the iodine is consumed by the thiosulfate ions. Thus, the end point is detected easily by noting the color change. It must be remembered that iodine, being nonpolar, is very slightly soluble in water. However, it dissolves in water in the presence of potassium iodide due to the formation of I3- ions. Let's revisit the redox reaction that we've seen. Here, we place a zinc rod in copper nitrate solution. After a while, the color of the solution becomes pale blue, and finally, it becomes colorless. The zinc rod, on the other hand, gets coated with reddish metallic copper. In this reaction, zinc is oxidized to zinc ions and copper 2+ ions are reduced to form copper. This reaction took place in an open vessel, and the chemical energy from the reaction was released as heat. Think about it. Is it possible to convert the chemical energy into electrical energy? Yes, it is. Let's see how. We place the zinc rod in 1 molar zinc sulfate solution. Then, we place the copper rod in 1 molar copper sulfate solution. In each beaker, the reaction takes place at the interface between the metal and its salt solution, and both the oxidized and reduced forms of the same species are present. This is also known as a redox couple. A redox couple is defined as a combination of the oxidized and reduced forms of the same substance taking part in a redox reaction. Now, we connect the two solutions by using a salt bridge. A salt bridge is a U-tube filled with potassium chloride or ammonium nitrate, usually solidified by boiling with agar and later cooling to a jelly-like substance. It is an inert electrolyte and is a substance whose ions neither take part in a redox reaction nor do react with the solutions in the two beakers. Next, we connect the two ends of a voltmeter to zinc and copper electrodes by means of wires. When the switch is in the off position, no reaction takes place and current does not flow. As soon as the switch is in the on position, current flows and the reading in the voltmeter changes, indicating that current is passing through it. The current is caused due to the chemical reaction taking place between the two beakers. Since zinc is a more active metal than copper, it loses electrons and gets oxidized. The equation for this reaction can be expressed as zinc atom loses 2 electrons to form zinc ions. The electrons move through the voltmeter wire and reach the copper rod. When the electrons lost by zinc reach the copper rod, they combine with the copper 2+ ions to form neutral copper atoms, which get deposited on the copper rod. The equation for this reaction can be expressed as copper 2+ ions gain 2 electrons and form copper metal. As the reaction continues, the excess zinc ions accumulate around the zinc rod in the zinc solution. Due to this, any further oxidation of zinc stops as the repulsion among Zn2+ ions increases. Similarly, copper 2+ ions reduce to copper atoms and deposit on the copper rod. This loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions in the solution. This prevents the further reduction of copper ions. As a result, the overall reaction stops and also the current in the setup stops. To avoid such a situation, the salt bridge plays an active role. The positive potassium ions move from the salt bridge into the copper solution, thereby neutralizing the negative charge. On the other hand, the negative chloride ions move from the salt bridge into the zinc solution and neutralize the positive charge. Thus, reaction goes on continuously till the solutions get exhausted. The reaction stops when either the zinc rod or the copper ions are depleted. The overall equation for the reaction is copper 2 ions react with zinc metal to form zinc 2+ ions and copper. Note that Zn loses electrons and undergoes oxidation, and hence the beaker in which zinc rod is immersed in zinc sulfate solution is called oxidation half cell. The electrode at which oxidation takes place is called anode. On the other hand, the beaker in which copper rod is dipped in copper sulfate solution, reduction of copper ions is taking place and is referred to as reduction half cell. The electrode at which reduction takes place is called cathode. During the cell notation, a slash is used to separate the oxidized form and the reduced form in a couple. The overall cell is represented by writing oxidation half cell on the left-hand side and reduction half cell on the right-hand side, both separated by 2 vertical lines. Electrons produced at anode due to oxidation of zinc travel through the external circuit to cathode, where they reduce copper ions. Note that the current flow is in the opposite direction to the electron flow. In this experiment, the two redox couples are zinc and zinc 2 plus ions and copper 2 plus ions and copper. The apparatus set up for this experiment is known as the galvanic cell. The galvanic cell was invented by an Italian anatomist, Luigi Galvani. Note that there are many factors that determine the amount of electric current produced by a galvanic cell. The most important factor is the tendency of a metal to lose electrons. Between the two electrodes, one has a tendency to lose electrons, while the other has a tendency to gain electrons. The potential of any electrode, commonly known as electrode potential, is the potential difference between it and the electrolyte surrounding the electrode. The electrode potential of an electrode depends on the nature of the metal, concentration of the ions, and the temperature of an electrolyte. If the concentration of each species taking part in the electrode reaction is taken as unity and temperature is taken as 298 Kelvin, then the potential of each electrode is known as the standard electrode potential and is represented as E0. By convention, the standard electrode potential of hydrogen electrode is taken as 0. Chemists have created a table that lists the tendency of various substances to lose electrons in a galvanic cell. Note that the values of standard electrode potentials are relative to the standard hydrogen electrode. A metal with a higher standard reduction potential can be easily reduced, and hence is a better oxidizing agent. For example, fluorine has a standard electrode potential of plus 2.87 volts, while lithium has a standard potential of minus 3.05 volts. Thus, fluorine reduces easily and is the strongest oxidizing agent. On the other hand, lithium undergoes oxidation as is the strongest reducing agent.